So good morning. We will start this section. This is course called statistics. Uh, so let me first of all introduce myself. I'm Professor Sarath Banneheka. I can write it here and then also I can erase it. So I can use the same place. So I'm attached to the Department of Statistics, Java. These days I'm on leave actually. We have something called sabbatical leave, so I'm on sabbatical leave these days. So, what are your names?
Maditya. Aditya.
Aditya.
Hasid.
Huh?
Hasid.
Hasid? Du. Right. I'm very bad in remembering names, but anyway. Aditya and Hasid, I think it will be okay for me at the moment. Right. So this is actually the textbook prescribed by Dr. Prof. And I happen to be a little familiar with this book because I remember when I was doing my master's at SFU, Simon Fraser University, Canada, I used to work as a teaching assistant. Like usually all graduate students do that to earn some money. So that's what we do usually, work as a teaching assistant. So during that time, there was one statistics course taught by a lecturer, professor. And I was the teaching assistant for that course, and this is the book that was used in that book. So I didn't teach from it, but students come and ask questions from it, and so on. So for a long time ago, that's what I brought my memories to when I see this book as the prescribed book for this course. Right. So as I mentioned, this book actually they have written in a way that mainly I think they have focused it for non-mathematics students. So that's why they have tried to keep all the mathematical stuff to a very limited amount, minimum. But I guess you are being mathematics students, you can handle more than that actually. Right. So tell me a little bit about your background. For example, what have you done? You have done your A-levels, I guess.
After A-level students, I got selected to University of Colombo Physical Science. I went to St. Peter's College, Colombo. That's it.
So you decided not to go to university?
I decided not to go to Moratu.
Okay. So you are still trying next time when you go, not to go to Moratu? You want to do a mathematics? But are you still already a student at Colombo University?
No, I just got selected.
I just got selected. Okay. What about you?
I'm also just got selected to Colombo University,
Ah,
but
okay.
not for mathematics, but for computer science.
Okay. Very good areas anyway. So you'll be going to the university. So what time will it be usually? We just got the announcement, right?
Yeah.
About the marks and so on.
Probably University of Colombo next year, April or May.
Yeah. Okay. So have you studied statistics at any point in your life in A-level and so on? Anything related to statistics? A-level statistics part, there were two sections, I think, probability and another part called statistics, right?
Yeah.
So you have done that?
Yeah.
Both? So I think you have done more than this book. Because those two contains, for example, probability part contains a lot of this, more than this, I think. But that's good because I know many teachers in the schools and also in tuition classes, these two sections are not usually covered, right? But if you have done that, very good. Yeah. So then we can discuss. I remember I will be doing this lecture in English most of the time because Dr. Bhat asked me to do it in English because we are recording it and he's going to put it on the YouTube. I think. But of course, if you feel like for some reason if you want to talk about in singular, that's welcome. Okay, no problem. I will answer in that case also singular. So singular and English will be both okay. Right. So if you have done statistics, so you may have some idea about what it is, right? So according to your view, what is statistics? No, just tell anything. I mean, whatever. You don't have to be exactly correct or anything. You can just mention, then we can discuss.
Analyzing big data and making predictions, something that you used to do that.
Right.
Something that helps you do that.
Yeah. Okay. What is your idea about statistics?
Gathering data and analyzing it to get future predictions. And
That's right. Okay. So you both are correct. But the big data word actually came very recently, right? So now there are several things: statistics, big data analytics. They are not exactly the same, but complementing each other. You can do big data analysis without statistics. But earlier days, we didn't have this many big data sets. Right? For example, nowadays we are always generating data. We are not actually collecting it. They are being automatically collected in most of the places. Like for example, telephone companies or supermarkets. Whenever we buy something, when we pay something, there is a bill, right? So that's data. Right? They are automatically generated in very large quantities, right? Very fast pace. So therefore, actually, from very recently, usual classical or traditional statistical methods were not enough to analyze these data, especially the computer power was not enough. So we need now, but anyway, when we have very powerful computers nowadays. So now we have people have created new methods to tackle that kind of data. So that's why usually for big data analytics, slightly different from usual classical statistical methods. Statistical methods are applied there, but in a different way than what we used to do. Okay, so I'll come to this book later. The first part here, it says design of experiments, and then there are two chapters: controlled experiments and observational studies. So I was thinking probably I will be able to cover both today. So I have prepared some slides. I'll give you the lecture note, for example, like this. I will give you this note at the end of the lecture. So this is actually the note version of the slides. But if you want, you can write down anything in addition to that during the class. But I will give you this note also at the end of the class. Right. So I'll start with actually a little bit of deviating from the book. I'll start with what is statistics, because that is important to know, right? Because they have not discussed in detail what is statistics. They have directly come to experimental studies. Right. So as I mentioned earlier, there's no particular fixed definition for statistics. What is statistics? Different people have different views. Like you two have different views. So among those views, there are few commonly accepted views. So this is one of the views. Actually, this is the view that is in the book. This is, if I open this in to make it full screen. So this is how Friedman and Pisani and Purves have described statistics. Statistics is the art of making numerical conjectures about puzzling questions. But I guess you may have earlier thought that it is a science. Right? But they say it's an art. An art of making numerical conjectures about puzzling questions. So this view contains a lot of ideas in it. Why is it an art rather than a science? Well, actually, it contains some kind of aspect of science also, but they have chosen to call it art mainly because it is not just like in mathematics, writing down equations and maybe putting numbers into the equations and getting some value and like that. There's much more than that. Especially, you have to have something called creativity, and also some kind of able to do some judgments based on the scenario and based on the data. And also, you have to have any statistician has to have skills for making numerical conjectures. Numerical conjectures means educated guesses. Conjectures are educated guesses, not wild guesses. It's kind of educated, logical, meaningful guesses, but numerical in terms of in the form of numbers. Right? So those guesses have to come in form of numbers. About what? About puzzling questions. So what do you mean by puzzling questions? There are some questions where the answers are straightforward, and sometimes we know exactly that answer is correct. Right? But we use statistics mainly to answer questions for which we don't have a direct answer. And even if we get some answer using the data and so on, usually they are not exactly correct, always correct. Right? So that is one important thing in statistics. Whenever we solve a problem using statistics, one important thing to understand is there is always some probability of error in our decisions. It's not like mathematics. So if you add 5 to 3, you know definitely is 8, definitely correct. But in statistics, you add 5 to 8, maybe it's not 8. 5 to 3, it's not 8. Right? It's not what I mean is it's exactly 8, but what I mean is there is a random component that usually involves in statistics, and therefore the answers are going to be also kind of random answers. It's where there is a certain probability that it is accurate, or at the same time, one minus that probability will be wrong also. Right? So what we do by applying these statistics is actually we have to be careful and good enough, skillful to first of all collect data correctly to answer the question of interest. Right? If you just collect data whatever the way you want, maybe those data may not be suitable to answer your question. Right? So first of all, you have to understand what is your objective. And then in order to answer that objective, you have to think of how should we collect data, what kind of data should we collect, and what is the design that we have to use to collect the data and so on. So that's something you have to decide. Once you have collected data, there is a process that you have to undergo. Usually when we collect data, they are coming in bulks. Right? There can be errors in the data and so. So there's usually an editing part of the data. You have to enter the computer into the computers. And then of course, when you are analyzing, there are so many different methods in statistics. There are so many methods to analyze data. But once you have fixed your objective target, then you should be able to select what is the most suitable method to apply to get answer to my question. So selecting the most suitable method and then you should be able to apply. Once you apply it, of course the computer will give you the output, and then you should be able to be skillful to interpret the output correctly. So therefore, it's a process actually. So that's why we say we are getting always the answers or the outputs as in numerical values. So they are numerical conjectures. Why it's conjecture? Because it's not a perfect answer always. It's a guess. It's an educated guess. Logical, reasonable, justifiable guess. Whenever you say guess, it means that it may not be correct also, right? There is a possibility of error. So that's why this definition is capturing all the an art because you have to go through a process where you have to think, right? Creativity is important. You have to make judgments according to what kind of data you have to collect and what kind of methods to collect and so on. And then once you collect the data, there is another part. So therefore, that definition is a very useful and actually is a very good. It's not a definition actually; it's a view. Right? So I have added few things to that view to explain it a bit more. Why it is an art? Why it is numerical conjecture and so on. So statistics is a discipline. Is a subject that requires creativity, judgment, and skill. That's why we call it an art. In making educated numerical guesses, that's what we mean by numerical conjectures, about aspects of what? The reality of some situation in the real world. Right? So we want to find out the reality, but usually using only a small set of data. So that is where the uncertainty to our results come usually, right? So there is almost always, when you are talking about a statistical problem, there is almost always, some kind of population of interest attached to it. Right? So we want to study some aspect about some population. The population means a large set, usually a large set of individuals. It can be individuals, or it can be animals, or it can be some items and so on. For example, in a production process, the manager may want to find out what is the process fraction of defectives. What is the proportion of defectives made by this process? So in that case, actually, we are dealing with we are even though we don't mention it, we are thinking about all the items produced by this process. Right? Out of that, what percentage are defective? So in that case, the question is actually, we can frame our question as finding a population proportion of defective items produced by this process. So the question is about a population proportion. We want to find out, we want to guess somehow. Right? So what we do is we select a suitable sample of products and then find out the sample. In that sample, what is the proportion of defective products? Right? That can be done. So then what we do is we use that sample proportion of defective products as an estimate for the population proportion. So that we are using the sample proportion as a guess for the population proportion. So that is a numerical conjecture. Sample proportion is a numerical conjecture. Right? So when we find out that, we have to keep in our mind always, not only in this example, in almost all examples is like that. So we are able to find out the population proportion of defective items. But we are getting the sample proportion of defective items. Of course, we are going to use that as a guess. But of course, there is always a difference between these two. Right? You are almost never going to get the exact population proportion as the sample proportion. There is a difference of this. So that difference is called the error of our estimate. So if the error is a small value, it's okay because we are going to use this estimate for some reason, some purpose. If the error is small, we can still use it without any problem, right? Most of the times we can still use it. But if the error is going to be large, then that guess or the estimate will not be very useful. Or if you use it, for example, you may incur some kind of loss, right, because of that. So therefore, we have to have some idea about the error, the size of the error. Right? If it is small, it's okay. If it is large, it may not be okay. Probably we'll have to use some other methods to get another guess. Right? But there's a question. Can you think about the problem here? Like I say, I want to find out I want to have some idea about the error in my guess, right? If the error is small, that's okay. I'm going to use it for my purpose. If the error is not large, probably I will not use it, and we will be using some other method to get a different guess. Right? So what is the problem here? So why? Can you see any problem here? Can we find out the error?
After the incident has happened, we can calculate the.
Okay, suppose I get a sample of 100 items, right? And then I inspect each item, and then I find out, say, 5 of those are defective. So therefore, my sample proportion of defective items will be 5 divided by 100. That's 0.05. So now I have my guess. So I am going to say, okay, in the population, in my process, about 5% of the items are defective. So that's what I am going to conclude. But this is not exactly correct. There will be a difference between the actual proportion of defective items, and this is my guess. So what is the error in my guess? What is the error in my guess? What do you mean by error in this case? Error is my estimate or my guess minus the actual. Right? The difference between my value and the actual value. That's what we call the error. Can we find out the error?
We don't know the actual value yet.
That's right. Right? We don't know the actual value. Right? If we knew the actual value, we don't have to go this far, right? That's what our aim was, right? Our aim was to find out the actual proportion. If we knew it, then we don't have to collect data and just do some estimation and so on. So this is a very important thing to understand. In statistics, whenever you get some answer, not only estimate, sometimes we do some other things. I'll come to that later. The conclusion is there is always a possibility of error. And important thing is we never know the actual size of the error, because we never know the actual situation. The real thing we don't know. Right? So if you want to find out the error, you have to know the real thing. If you know the real thing, you don't have to use statistics. Now, but so that is a bad thing actually. That's a weakness kind of thing, but we cannot avoid it. But on the other hand, even though you don't know the actual error, right, as I mentioned, if the error is small, that's fine. If the error is large, that's not very good. But even though we are not able to calculate the actual difference, it may be enough sometimes to say something like this. For example, if I can say something like this, there is an error in my estimate, but I know that the error is less than 2%, and I am 95% sure about it. I am 95% sure that my error is less than 2%. If we can say something like that, then it gives you some idea about the error and how confident you are about it. Right? So the good thing about statistics is we can make that kind of statements, even though we cannot get the actual error. We can make some probability statements related to the error, so that we can get some idea about the error. So if that is enough, then we can apply. If you are 95% sure that the error is less than 2%, then the person will decide whether that is enough for me, accurate enough for me, and then we will use. Right. So that is called, actually we will learn about that, that's called confidence intervals. We can calculate some confidence intervals. Right. It's a way of measuring the accuracy of the result. Right. So like that, statistics can be applied to solve a lot of problems, but always you have to remember, whenever you use a sample of data to make some guesses, we call them statistical inference. Those guesses that we make are called inference. We infer about a population based on a sample taken from that population. We call it infer, and the things that we get are called inference, right? Statistical inference. So that is statistical inference is a very important part of statistics. Actually, statistics, all the techniques that we use to solve a lot of problems in statistics can be mainly divided into two areas. One area is called descriptive statistics. Descriptive. Right. And that is what you usually learn. Some of that you are usually learning at the A levels. Right? Finding out the mean, median, mode, standard deviation, sample quantities, and then drawing different, preparing different tables, frequency tables. For the sample, right? You get a sample of people or items or whatever, then you get the data from them. And then, in order to understand about the sample of data that you have, you prepare certain things, you do something, you calculate certain things. Those are called descriptive statistics. Right? But the main objective in most of the situations to collect data is not only to stop there. Right? We usually look at descriptive statistics to understand the situation, and by looking at that, then we can think of what are the suitable methods to do more analysis. Right? Usually, we have to do more analysis to extract the information in the data to answer a specific question about the population. Right? Remember, we usually, in almost all statistical problems, our aim is to answer a question regarding some population, some aspect of some population. Right? So that you have to keep on mind. Sometimes these populations can be really existing and finite populations. Right? For example, you may be interested in finding out how many students in a university need welfare. Right? How many students have in their families income less than a certain amount. What is the proportion, for example? Right? So in that case, the population is the set of all the students in your university. So you are interested in a population proportion. That is called a parameter. In statistics, that is called a parameter. Some quantity which you don't know related to the population. Right? A fixed value, unknown numerical value is called a parameter usually in statistics. Right? So the same word parameter is used by some other disciplines in some other meanings. For example, I have seen that engineers use this word for some other meanings also. Right? They, what we call variables, they call parameters sometimes. So this meaning of this word depends on the discipline that you are in. So in statistics, this word parameter is used usually to mean some unknown quantity, unknown number, unknown value related to some characteristic of a population. So in statistics, most of the times, we are going to either estimate, that is to guess, get an educated guess about one or more parameters. So that is one commonly occurring problem in statistics. We want to find out certain constants related to population using a sample of data. For example, we are interested in what is the unemployment rate. So that's unemployment rate for the population of Sri Lanka. So there is a population. We are interested in unemployment rate for the population of Sri Lanka, not for a sample. Right? What is the birth rate? Right? So those are usual statistics that are handled by the Department of Statistics and Census and Statistics. And in addition to that, of course, there are so many other things. Right? For example, one might say, what is the proportion of colorblind people in Sri Lanka, or maybe in a certain office, certain organization, maybe manager is interested in finding out what is the proportion of colorblind people in my employees. Maybe colorblindness may be a problem in that case, so he wants to find out and then maybe give some solution to that. So like that, there are situations where you are interested in some quantities and they are called parameters. So estimation of a parameter is one particular type of statistical problem. The estimation can be in two forms usually. In the previous example that I mentioned about the proportion of defective items in a production process. Right? So that is a parameter. Parameter is the proportion of defective items in the population, in the process. So if you just get a sample of items and then calculate the sample proportion and use that as a guess for the population proportion, that sample quantity is called the estimate. Right? So there is a way of estimating. In this case, actually, we don't have to use a particular method, but it's not always like that. Sometimes we cannot just get the sample quantity and calculate the sample proportion or sample mean. We have to use some other techniques to get an estimate. But anyway, estimation is a big part of statistics. Now I'm talking about the second part, that is the inferential statistics. Statistics has two parts: descriptive statistics and inferential statistics. Descriptive statistics is dealing with the sample only. They find out what is the sample mean, sample standard deviation, right, and so on. But using that sample, if you want to make some guesses about the population, then we have to use suitable methods. Those methods are called inferential methods. So when we talk about inference, there are mainly three things that we look at. Because any statistical inference problem can be converted. Right? Usually these problems are brought to us by clients. Right? They are not statisticians always. Right? They can be coming from different areas. Right? So they come and explain us the problem. But as statisticians, what you have to do is we have to, that is where the creativity comes as an art. We have to convert that into a statistical problem where we can tackle. Sometimes we may be able to convert their problem exactly into a statistical problem where we can solve and get an answer. If that is the best thing if you can do. But most of the times, unfortunately, we cannot convert that problem exactly into a statistical problem. We can maybe reduce or modify a little bit so that we can solve it statistically. But still, the answer will be enough for them. So our answer will not match exactly what they want, but still they can get us some idea. So that's where the creativity comes, right? You have to use, for example, suitable models. Right? They don't have any idea about models when they come, right? So we write down some mathematical models using our creativity, and then in the models there are unknown quantities. So we have to estimate those quantities. So that's where the estimation comes. Models contain, for example, there are something called regression models. If I write down here, so for example, I'll come to these things later. Right? When you write down something like this, for example, alpha plus beta x, right? You identify this one, right? Because in the straight line equation, right? Suppose you have two variables, x and y. They want to find out what kind of relationship is there between x and y, and they want to be able to predict the value of y when they know the value of x. So if that was the objective, usually we go for this kind of method. We try to build up a mathematical equation for the existing relationship between y and x. So what we can do is actually, if they have data, if they have, for example, paired data, we will first of all draw a simple graph called scatter plot. So for example, suppose for each xy pair, when you plot, we get this kind of graph. So you might think there is some kind of, we can approximate this thing using some kind of curve, right? Or it can be a straight line. For example, the data may be around a straight line. So if you think, once you draw this kind of graph, if you think the data are around a straight line, you will come up with a model like this, but there will be some other term, because alpha plus beta x is actually the straight line. Alpha plus beta x is the straight line. Right? But the data are not going to be on the straight line. So they are going to be either above, below, like this. Right? So there is always some other term you have to add to get the y. Right? Straight line plus or minus the. So your model will be like this. This is called a linear model, for example. Right? Or if you think it's a quadratic or maybe cubic type model, then you can use your mathematical knowledge. You know the general form of a quadratic formula. You know the general form of a quadratic cubic formula, and so on. So you assume, you make an assumption there. You make an assumption. Assume that the data are around the straight line, and therefore we are going to, instead of we can actually find out exact function that goes through all the points. Right? So we usually cannot do that. What we do is we find out some approximation for that. So there, when you write down this model, it comes that alpha and beta. Like if you think that, for example, this relationship is straight, it's a straight line relationship, then the model will have these two quantities, alpha and beta. Unless we know the alpha and beta, we cannot do anything using this model. Right? So as far as this model is concerned, alpha is a parameter. This model we are writing for the population. Even though using the sample we get an idea about what kind of relationship there exists, what we want is actually a model for the whole population. So there is a population formula. In that population formula, alpha is a parameter because it's a constant, but we don't know the value of it. What is the most suitable value for alpha? If you consider the whole population like this, what is the most suitable value for beta? If you consider the whole data, like usually we cannot get the whole population data, but if you do that, then you assume that you will still see this kind of pattern. So then the question is, what will be the most suitable value for alpha and beta, so that when we use it to predict something, our error will be as small as possible. That is the objective. Right? So we want to get some formula so that when we are using it, the error, right? Always when you use for example, suppose you get some value like 5 for here, 7.5 for here. So you get some values using some method. But that will not give you the exact value for y. For example, even for the sample data, if you have this 9 here, right? Suppose that is the 5 plus 7.5x. So this y value is not exactly this value. Right? So there is an error. So in this case, error size is, this is a positive error, some small value. In this case, this is error is smaller than this one in this case, but still is positive. Here error will be negative and so on. So we want to find out some method to find out the most suitable value for alpha and beta, so that not individual errors. Again, we cannot make individual errors to be as small as possible. We will be looking at on average. As an average, getting the small errors as small as possible. Right? So people will have developed similar method. For example, in this case, we have a method called least squares method. We will talk about those things later. Right, so I was telling that so estimation, like this one, in this case, in the model there are parameters, or in a situation like you want to estimate the proportion of defective items in a process, or maybe the proportion of colorblind, or maybe the mean income of people in a village, like that, different things related to population. Those are all parameters, unknown but fixed values. So estimation in one is one point. So this estimation that we are getting some values for those, that is called actually point estimation. Point estimation. Right? And another version of estimation is interval estimation. As I mentioned earlier, you will, for example, get some estimate for the population proportion of defective items, say you get 5%, that's your estimate. And then you are able, if you are using the correct methods, you will be able to get some probability statement regarding the size of your error. Right? You will not be able to get the exact value of the error, but some probability statement regarding the error, saying, for example, I'm 95% to 99% sure that the error is less than 2%, for example. So that leads to getting something called confidence interval. That item, that statement is the same as saying, for example, the actual population proportion is between 7% and 3%. If the error is within 2%, then actual estimate is 5%, then the actual value will be between 7% and 3%. Right? So I'm 95% sure that the actual error is between those two numbers. So we can say that get some confidence interval for the error, or we can get a confidence interval for the actual population proportion. Right? So that is the interval estimation. Those are very useful in making decisions in different areas, right? In different situations. For example, we know that even if we go by a car, for example, there's always a chance of some accident, right? But still, we all travel by vehicles, right? If we knew that there is a very high probability of having an accident, we will not use vehicles. We will go by walking. But we know that there is a chance, but by in this case we have not calculated something, but by experience we know that the probability of an accident when you are going by a vehicle is not very small. So still we are taking that risk. So in that case we think that that error is small enough for us to use the vehicle. So like that, when you have some idea about the estimate, accuracy of your estimate, and the size of the error in the probability statement, right? So in a probability sense, then you can make a decision whether you want to apply it or not. Suppose, for example, our father, for example, is planning to sow some paddy tomorrow. But then he hears that there is going to be rain tomorrow with high probability. It's a very likely chance that there will be rain tomorrow. So then, okay. So then he will not probably sow paddy next tomorrow. But on the other hand, if you hear that like every day we are hearing these kind of things, nobody cares about these predictions or weather predictions. Right? Sometimes he may not deal with that, and he will go and sow the paddy, and probably there will be no rain also. So no problem. Right? But anyway, that whether he wants to go ahead with that or not has to be depend on the forecast, right? And how accurate the forecasts are, as we know from our experience, right? You can ask any questions actually when I'm explaining. If you want to ask any question, please stop me and ask. Right? So here I have just explained the same thing. Why we call it an art, and why we call it an art that requires it's an art of making numerical guesses and so on. I have written down a few sentences to explain that. When you get the note, you can read it. Right? So, as I mentioned, you have to be creative in thinking a way to solve the problem. Whether you want to build up a model and then use a suitable model method to feed the model and then use it, or maybe whether you can just draw a graph and then look at that and make a decision. So like that, you have to be creative. And also in statistics, usually we use the methods that have been already constructed or come up with different people. There are built-in methods, right? Well accepted methods. Right? So usually we have to use one of those methods to solve our problem. Right? So this selecting the most suitable method to solve our problem is actually not an easy thing. Because these solutions have been made by people, the methods have been created by people always under some assumptions. If you can assume this and this and this and this, then this kind of problem can be solved using this method. But if you cannot assume that kind of, make that kind of assumption, then that method is not suitable. Maybe some other method is available for your situation. So therefore, it's not an easy thing to decide. You have to know a little bit about these things, right? You have to know the methods, commonly available methods, and also you have to know what are the underlying assumptions they have made when they are producing these methods. People always do research, right? When they come up a method, come up a problem. If there is no available method to solve that particular problem, then under their situations, under their conditions, they think of what is a suitable method and then they publish it. So that becomes a common method after that. Right? So like that in our problem, when we have some problem, maybe our situation matches to one of those situations where they have assumed what they have assumed. In that case, we can directly use their method. But if our method doesn't match, and if our situation doesn't match to one of those assumptions, then still we can apply, of course. We can ask the computer to go ahead and analyze the data, but our conclusions will be wrong in that case. That is what is happening in most of the times actually. People don't think about what are the underlying assumptions. They know one method to solve a similar problem, they just apply it and get some answer and then write down. And actually what happens in the even in our university, I have seen people have published some papers. Even statistics lecturers have published some papers. So published means there are errors. They are in their interpretations, there are errors. So that means the lecturer doesn't know that is a wrong thing, and the reviewer also doesn't know. It has been published. Very simple things. So this is very important thing to notice that people sometimes don't care. They just apply and some people think that any method is okay. No, it's not like that. So assumptions are very important, and before applying certain methods, we have to actually check whether those assumptions are reasonable in our situation. So for example, in most of the situations, there is an assumption that your data are normally distributed. There's something called normal distribution. We'll come to that later. So most of the classical methods have been developed earlier days. Nowadays, because most of the data are actually not normally distributed, therefore those methods cannot be applied. So now people have come up with different other methods to deal with other kind of data. But still, most people know only those classical things. So they always use those methods, assuming that the data are normal. But the data are not normal most of the time. So their conclusions are wrong. So therefore, selecting the suitable method under suitable assumptions is reasonable, very important in statistics. Right. So I mentioned what is a numerical conjecture is. Conjecture means educated guess. It's a reasonable guess. It has to be logical. There should be a base for your guess, right? It's not a wild guess. In statistics, most of the time, first of all, this guess comes in the form of a number, and then of course we have to interpret it, because usually when the client comes, he gives the problem in words, we convert it into a statistics and mathematics and solve it, and the result comes in a numerical form. The client doesn't understand that, so we have to then convert it into their language. We have to interpret. So that is the process actually. So these numerical conjectures in statistics usually come in the form of new numbers like probabilities, like confidence intervals are 90% confident, 95% confidence, that is the number, right? Estimates, confidence intervals, and there is another part in statistics. Now I mentioned about the point estimation, interval estimation, we both come under estimation. And then there is another very important part called test of hypothesis. Test of hypothesis. So more big part goes to test of hypothesis. A hypothesis is a statement regarding one or more parameters. Again, it's about a state about parameters. It's a statement about some unknown phenomenon. For example, one mind is a guess actually, kind of a guess again. It's a conjecture. It can be a conjecture also. For example, one might say, okay, suppose during the election period, we always hear that everybody is saying, I'm going to get this much vote. I'm going to get more than 60% vote, right? So he is talking about the population proportion of votes that he will be getting, right? Or he is talking about in that case, in the population, there are 60% of the people who will be voting for me. That's what he means. Right? So that is a kind of a hypothesis about the population proportion of people who will be voting for him. There is an actual proportion of people who will be voting for him, but we don't know that one. So he's talking about that value. He's telling that value will be greater than 0.6, 60%. So that is a statement. So my population proportion of voters who will be willing to vote for me is greater than 0.6. So that's a statement. So that kind of statement is called a hypothesis. Now we can test whether this hypothesis can be accepted or rejected by just collecting some sample of data. We don't have to go and ask everybody in the population whether he is going to answer vote for this person or not. Right? Just by taking a suitable sample based on the sample proportion of people who will be voting for him, we can test that hypothesis. Right? So there again, our conclusion can be erroneous or our conclusion can be correct. So there again we have to use suitable methods so that the probability of making an error is as small as possible. So hypothesis test can be regarding one parameter like that, or maybe there can be a hypothesis, for example, saying there are two treatments for the same ailment, say for example headache. Right? Suppose there is already existing on the counter tablet like some paracetamol, for example. Right? We know it's a remedy for headache. Suppose somebody has come up a new painkiller and he says this gives you relief quicker than paracetamol. Right? So we can test that. Right? He's talking about the time that is taken to get relief. Right? So there is a time will be of course different for person to person. So therefore we have to maybe look at one quantity instead of individual values. We will have to look at maybe mean of those values. Right? What is the mean time taken to get relief when you take paracetamol? What is the mean time if you get the new medicine? Right? So you can compare these two means. Right? If the mean for the new medicine is smaller than the mean for the paracetamol, then you think the second one is quicker. Right? So there is a hypothesis there. So for example, say mean 1 is population mean 1 is the mean for the paracetamol, and mean 2 is the mean for the second one, new drug. Right? So these mean 1 and mean 2 both are parameters. We don't know the actual values for the population. Right? So we want to test whether mu 1 is less than mu 2 or mu 1 is greater than mu 2. So there are two statements. One is the opposite of the other. So we collect the data using a suitable test. Now we are going to talk about that kind of experiments. There are how to carry out an experiment to answer this question. So using the data, you can check whether this statement is more likely to be correct or whether the other statement is more likely to be correct. So based on that, we will make a decision. So that is, but remembering that decision can be erroneous also because we have made a decision based on sample of data, not about Right. So I have explained these things already. Right? The way is that actually I have never taught a lesson from a textbook like this. So if you're teaching from a textbook, usually you don't teach like this. You have to go by the textbook. But now I am going everywhere. But I think that is the way that I teach actually. That I don't want to just teach the things in the book only. Right? So you have to have some knowledge, broader knowledge. So therefore, this is I think the way. But I'm coming to this thing. I'm trying back to the So here I have given some examples, right? Some puzzling questions. Right? These are very simple actually, but still puzzling, right? Does this new drug really work better than the old one, like paracetamol? So when you answer this question, you have to be creative. Why? It says, does this new drug really work better than the old one? So first of all, we have to define what. What do you mean by really work better than the other? What does that mean? Right? You have to quantify that. So you have to, for example, define to some quantities. Right? Say, suppose mean M1. So for example, usually we use these Greek letters to denote these parameters. So you have to actually build up a statistical problem. Right? The question comes like this. Does this new drug really work better than the old? And then we have to formulate that problem into a statistical problem, which can be tackled using available methods or new method. Right? So you have to define, for example, let say mu1 is the mean time taken to give relief from the old method, old drug, right? And say mu2 be the mean time for the new drug. So you first of all define two quantities. You are not going to look at individual times. You are now reducing your problem to means. You are going to compare means, right? And we will say new one is better than old one if mu2 is less than mu1. Right? So we now write down our problem in terms of these. We will say the second new one is better than old one if mu2 is less than mu1. So that is our problem now. So we want to test whether mu2 is less than mu1 or whether mu is greater than mu1. So the problem came in that way. So we reduce it to a tackleable problem. Now, in order to represent the variable time taken to get relief into a certain constant, mean. So then we will be comparing means. So like that. So that is where you have to be able to create, because the client doesn't give you these details. We have to create our problem statistically like this. So in this case, we are going to test something like hypothesis. We usually write down something like this. We come to this data. For example, mu2 less than mu1 versus h1, the other one for the alternative hypothesis, and mu2 greater than mu1. So we will be testing this hypothesis versus this hypothesis using a sample of data that we collect using some experiment. In this case, we have to do an experiment. As usually, I'll explain these things in detail later on. Usually, the equal sign comes with this one because this statement has to be the complement of this statement usually. So equal should be somewhere there. So usually equal comes with this one. Right? So that is that's called test of hypothesis. In this case, regarding two parameters. And if you ask what will be the unemployment rate next year, that is a forecasting problem. Unemployment rate. So we may only know the variables on which the unemployment rate depends. Right? So maybe we already have some data in the past for those variables, and then using those, we may be able to predict the unemployment rate in the next year again. That's a prediction, that's an estimation. That's an estimation. But we use usually something called time series methods, because in this case we have to apply the data collected over time, right? Using the past year's data, we have to predict the future. Right? So in that case, we use something called time series methods to predict something like this. Is the production process in control? Right? So in a production process, there are two words. We say sometimes the process is in control, sometimes we say process is out of control. So the quality control engineer may ask, say, we want to find out, we want to derive or construct a method to find out whether the process is in control or out of control at a given time point. We have not set up a process control method yet, but we want to come up with a new method to decide whether the process is in control or out of control at a given time point. So this will be the problem given by the client engineer to the statistician. So then statistician has to first of all clear the question. First of all, we have to know what you mean by a process is in control. If you don't know that, we cannot test whether it's in control or not. So we first of all have to know what we mean by in control. The process is in control. What do you mean by process out of control? So first of all, you have to again statistically define this statement about the process is in control, so that we can test whether it is in control. Right. So usually, for example, suppose you are filling some bottles, drink, say for example, to some bottles, the target volume in a bottle is say 400 milliliters. Bottle target is that, but we know that usually almost always the actual amount in a bottle will not be exactly 400 milliliters. It will be less or above. If it is less or above by a very small amount, that's okay. Right? But if it is consistently less by a large amount, then there will be a problem, because people will complain. The bottle says 400 milliliters, but it has only 350 milliliters always. I told around that. But you are charging for 400. That will be a problem. Or if it is filling more than 400, going up to the cap always, that will be a problem in terms of the company, because it's going to lose something. So that's not a good thing. So therefore, you have to check whether so in that case you have to again formulate the problem. What do you mean by the process is in control? Okay, we will say process is in control if on average the actual amount is equal to 450. With a small deviation. Then we will say process is in control. Otherwise, we will say process is out of control. So then our question becomes, we want to test whether the mean level of the actual amount of drink is say 400 with a small standard deviation. So we will be testing about the mean and the standard deviation both of this actual amount, and then if it is in acceptable level, we will say process is in control. Otherwise, we will say process out of control. There again, we have a hypothesis problem. Hypothesis. Right? So this is usually done by using something called control charts. Control charts are actually a graphical method of hypothesis testing. Right? Because people working in those places don't understand statistics. Right? So they cannot work with the equations and so on. So what they do is they draw some graphs, right? Usually these are now automatically done, right? Automatically drawn. So then by looking at the graph, they can say whether the process is in control or out of control. So it's easier, much easier than calculating something and making a decision. Right. And the last one, how to adjust the marks of different subjects for their difficulty levels. How to adjust the marks. Now you all were selected to the university based on Z. So do you know why this Z score is calculated? Do you know how it is calculated? How do you?
How your mark subtracted the mean value divided by the standard.
Yeah, so everybody is doing 3 subjects now. So every student's mark for each subject is standardized, right? So from your mark for physics, for example, standardized by taking away the mean of physics and divided by the standard deviation of physics. Right? And the chemistry marks is like that, and mathematics marks is like that. And then you have 3 values, 3 Z values, and then take the average of those 3, that is yours is. But do you know why it is done? Earlier days, for example, my days, we didn't have Z scores. We were selected based on the aggregate. I have some marks for physics, I have some marks for chemistry, I have some marks for maths. We had 2 mathematics in those things. So we had 4 subjects. They add all 4 subjects marks, and then based on that they were selected. So do you know why it was changed to Z score?
Then you'll get the ones with the highest ranks, you'll get the highest marks for the highest toughest subject.
Yeah, that's right. Right, because they thought that there are different subjects too. There are different subjects, but sometimes it's possible for doing different combinations. You can be selected into the same degree program. Right? For example, say biology, chemistry, and physics. If they do it, they can come to biology degree. They can do a biology degree. First of all, they will go to medicine and so on. Otherwise, they can come to do biology. Right? Physics, chemistry, biology. And also, if somebody does, instead of physics, if somebody does agriculture, chemistry and biology, they also can come to the biology degree program. So some people thought agriculture is easier than physics. The other 2 subjects are common. So this is the 3rd subject, which is different. And one is easier than the other one, and therefore they thought those who are, if you are getting the aggregate, if you are looking at the aggregate marks, total marks instead of Z score, most of the agriculture students will have high marks, and therefore their total will be higher, and they will have a high chance of being selected into biology degree. So therefore they thought that's not fair, right? By doing an easy subject, they get higher chance of being selected. So this was a problem that they discussed. And as a solution, they came up with the Z score method. Some group of people discussed, and they suggested this method, Z score, as a solution. Right? So, therefore, what we can understand is they use this Z score method as a solution for the problem of having different subjects people coming to the same degree program. So, it's kind of an adjustment for the difficulty level. They wanted to adjust for the difficulty level. For example, they thought that if you adjust so that somebody get 80 for agriculture, and if you get say 75 for physics, they should have the same value instead of 2 values, right? Because physics is difficult. So something like that. Right? Less mark for physics should be equal to some high mark for agriculture, because agriculture is usually. So, with that idea, they came up with this method, Z score method. Actually, unfortunately, I have to say, they have done a blunder. What they expected that Z score will do is not actually happening. Nowadays, I am doing some research regarding this, and I'm pretty sure that Z score method is not solving that problem. And actually, Z-score problem has worsened that problem in some situations also. Worsened, not solved. But still nobody is accepting that because many people cannot actually think even what is this. They don't know. And because some people who are called statisticians and high-ranking statisticians propose this method, so they are just believing it. Nobody is willing to think more. But I can actually show that this method is not the solution for that. Actually, I don't have a solution at the moment. I think at the moment the best solution is the previous one. Right? Just go by this one because those who select agriculture or those who select physics is their choice. Right? If somebody selects physics, he could have chosen agriculture if you want. Right? If you know that it is easy, and if you want to get easy marks, he or she would have selected that. Right? So at the beginning, they have the choice. Right? Once they have given the choice, it is unfair to after that once they get the marks to adjust that is unfair in my view. We didn't force those people to do physics, or we didn't force those people to do agriculture. It was their selection. Right? Everybody is free to select any subject. Right? So once you are given that choice, we should not do any adjustments to the mark. We have to just consider the marks they have got. Right? Because actually, there can be some solutions, but still they will not be 100% correct. There will be always some people who are going to be disadvantaged. Right? So these are very important questions to answer. Not just transforming your marks into something else. You have to think with it. You have to show that actually that method solves the problem. So there was a problem. Somebody thought that this will solve it, but nobody checked whether that actually solved it. Right? Because some expert, so-called expert, suggested it, everybody else has accepted it. So that is actually regarding Z-score. Okay, so that was actually the view in the book. Do you want to take a small break? How do you take break usually? 10 minutes. 10 minutes. View that we usually learn in science as a science subject. Statistics is a science of collecting, analyzing, and interpreting data. Earlier we said it's art. Right? So this view actually focuses more on the process. Right? So statistics, whenever we apply statistics to solve a problem, it's not just a single thing, it is a process. Right? You have to collect the data and then analyze the data and interpret the data. Right? So this view actually emphasizes on the process aspect of statistics. Right? So as I mentioned earlier, collecting data, earlier days we used to mainly do two ways. Collecting data is done in two ways. One is called experimental type of studies. The other one is called observational studies. Experimental, observational. Right? But now we have automatically collecting data. Right? None of those two. Right? Automatically data are coming in vast volumes and vast speed and varieties. So that's where the big data comes. But we talk about statistics, still we are talking about the collected data, right? Using experiments or observations. In the experimental studies, the person who does the research has some control over the data collection method. For example, if you are comparing two treatments, for example, paracetamol and new drug, the researcher decides who is going to get the paracetamol drug and who is going to get the other. Usually it is done randomly, but still doing randomly is done by a person. Right? So there is a personal intervention in the experimental studies. But in observational studies, we don't decide who gets which treatment or who get what drug or whatever. It's naturally selected already. Right? For example, suppose we want to find out whether smoking is related to lung cancer, right? So it's not possible for us to ask some people, okay, you people start smoking, you people don't smoke, and then we will observe you for some years, and then at the end we will see how many people got lung cancer, and so that is impossible, right? So, but there are already some people already smoking, some people already not smoking. So we have two natural groups there. We can just observe these two groups, and then based on sometimes we can come up with decisions. But there are certain important things that we have to be careful. We talk about those things, usually called confounding and so on. But those are the two methods that usually used to collect data in statistics, right? Observational studies and experimental studies. And then analyzing means again, you have to usually analyze the sample itself. That there we use the descriptive analysis, and then of course we use some inferential methods to make some inference about the population. Those are the methods that we use to estimate, like point estimation, interval estimation, and hypothesis testing. So once you choose the suitable method and apply it, you get results. Nowadays, of course, we don't do these things manually. Always we do using computers. So always computers give you some values, right? Outputs. So when we should be able to, statistician first of all should be able to understand what those values are, and then should be able to interpret those values so that the client can understand it in their language. So this is a process, therefore, when you are talking about statistical solution to a problem, it is not a single thing, it's a process solution. So I have added few examples here. In a medical study, for example, suppose doctors record blood pressure readings of 200 patients, so that is the collecting data. And then of course you have to analyze, people may calculate some means and so on, averages, right? And then if they want to compare treatments, they will look at the blood pressure of people who don't get the treatment and who get the treatment. Usually these two are called treatment group and control group. Treatment group and control group. So then they will compare the mean blood pressure levels, and then based on that they will come to decisions. Right? So there again they will be testing a hypothesis, for example, whether the mean blood pressure level of the treatment group is smaller than the mean blood pressure level of the control. So here I have given a few examples. You can go through them when you look at the note. For example, business field, collecting company, a company gathers monthly sales, and then using those things we can predict. First of all, we can see whether the sales are going up or going down. So that's called the trend, the general direction where it is moving. Right? Of course, there will be ups and downs in depending on the season. For example, jewelry sales usually go up close to May and so on, because those May and so on considered as auspicious months, right? Usually, a lot of weddings are around that period. So during that period, usually jewelry sales can go up. So there's a seasonal variation, right? Or maybe some other rasakavili, right? Sweets sales will go up during Christmas period and also Sinhala period and so on. So those are seasonal variations. But maybe due to the population increase, usually it's going up always, right? But with that there will be variations. So we can see these variations, and using the information that you get, you can do some prediction. What will be the demand in a certain month and so on. Okay, these are just examples in different fields. Education, for example, a teacher may record the exam scores of students and based on that, they will calculate some few descriptive statistics like mean, median, and the standard deviation, and so on. Based on that, so the person has, for example, the marks for each question. So they can look at, okay, question-wise mean, question-wise standard deviation, and so on, right? So from that, maybe they can understand, they can identify which questions were more difficult for these students and which questions were more easy, right? So for easy questions, usually the mean marks will be high, and the variation will be very small, right? Mean marks will be very close to some value. So mean will be high and the values will be close to that. But if a question will be difficult, if the question is difficult, usually the marks are small, but there will be a variation, big variation, right? Of course, there are some good students, they will have high marks. Very weak students, so difficult questions will be very difficult for them. So the marks will be maybe in the range of 10 to 80 for that difficult question. But the mean will be maybe 40 or so. So like that, but by looking at these things, teacher can identify which topics were more difficult for the students, and therefore when maybe teaching, he or she can be focusing on those things more, right? When they discuss, do the revision and so on. So they can be used in that way. So that is one another view of statistics is the science of collecting, analyzing, and interpreting data. So there is another view. Statistics is the science, again say science, science of decision making under uncertainty. Decision making under. So always actually we use statistics to make some decision. Right? We just don't do a descriptive statistics and stop there and just record them. Most of the times we apply statistics to make some decisions, important decisions. But we have to keep in mind that these decisions can be correct or wrong, as I mentioned. But if we have used the most suitable method under the correct assumptions, then we can be confident with a high confidence level that our method will give the correct answer. But of course, we have to keep in mind that there is a small probability of errors also. So that's what I mean by uncertainty. Actually, uncertainty can come in two ways. First of all, in the data there can be uncertainty, and in the decision also there can be uncertainty. Uncertainty means in this case, they are when we talk about uncertainty in data, they are not sometimes the actual values. Sometimes people will give you wrong answers, right? If, for example, if you ask what is your income, he or she may not give you the correct answer at all. Even if, for example, suppose you are measuring something, your value that you get can be slightly above or below the actual value. Right? If you are measuring certain things, right? Suppose you are measuring the amount of milk obtained by a cow. Right? There is a certain amount that you get on a day, but actual value may be due to measuring errors or some other reasons. There can be errors. So that's what you mean by uncertainty. Right? Uncertainty is there, possible error is there. Right? So all these errors. As far as the errors are concerned, there are different types of errors. Measurement errors, and due to measurement errors and also recording errors. When you record them, there can be errors. So due to different type of errors, and finally, the answer can be in that case bias or can have a large error. Right. So it's a science. Because we use some systematic methods, scientific methods, right? Therefore, it's a science, right? For example, in a medical trial, researchers collect data in a controlled way. We are going to talk about these controlled experiments in the first chapter. Analyze it. So, when we apply, for example, if you go to test whether a drug is effective, right? In this case, generally we say we give the drug to one group and something called placebo to another, and then compare the maybe the proportion of people who got better. Right? That's what we generally say. But more than that, actually, we have to be very careful in doing this kind of experiments because there can be a lot of problems otherwise, making the results invalid. So we'll talk about those things later. So that's why we say we have to use some systematic method, scientific method to avoid problems when you make the decisions. So that's why it makes a science. So uncertainty, as I mentioned earlier, it comes in data as well as ratios. Okay, so we looked at three versions of statistics. Explanation of statistics. The first one said it was art with good reasons, and then the other two said sciences gave with good reasons. So I have blended actually all these three views and come up with this idea here. Statistics is a blend of art and science, helping us to make sense of uncertainty in real world problems based on data. Right? It's an art because we need the judgment and interpretation. Right? It's a science because we need mathematical methods, mathematical review and probability theory, definitely. So that becomes it's a science, right? Helping us to make sense of uncertainty in real world problems based on the data. So that can be considered as another view. Right? So I think that is enough as kind of a what is statistics. So we try to answer the question what is statistics. And then I thought maybe it's also good to talk a little bit about the other terms nowadays we are using with something related to statistics, as you said, big data. Right? So statistics is the old idea, right? When we analyze the data, we always talk about statistics. But in that kind of situation, the data, the amount of data that we were dealing with, was not that very large. It was not that large. Right? They were manageable sizes. But as the technology improves now, data are generated every second in very large amounts in various places. All statistical methods are not enough to deal with that. Computing power is not olden days. The computing power was not enough, but now we have powerful computers, so we can deal with that data. So, so in the field now there are different words, right? So statistics one is the old one. Now we have a word called big data. Related to that, there is something called machine learning, and combining these things, there is something called data science. So data science is a big word. It's a combination of all these things. So I have added few slides explaining these things, and there are some differences and similarities. Right? So statistics, as I mentioned, is a discipline of drawing conclusion from data under uncertainty. Usually when we see data, in this case, it's a manageable size data. In statistics, we emphasize on the inference, right? As I mentioned, estimation, it can be a point estimation or interval estimation or test of hypothesis. When you look at the output, typical outputs, usually we have, of course, the estimates are there, and then with that, there is some output always that gives you an idea about the error size. There is something called standard error, giving you an idea about the error size. It's not giving you exact size, as I mentioned. Exact error size is impossible to find always, but you can get some estimate of that, or you can get some probability statement, confidence interval statements. Those are the outputs in statistical analysis. So the main role in statistics in all these things is actually even in the machine learning and in the data science, statistics provides the theory, right? Statistical theory, probability theory, and so on. Right? So statistics is actually a backbone of all these things. Without statistics, you cannot talk about data science. Right? And then big data is actually about big data. Right? Usually, big data is characterized earlier days. It was characterized by 3 V's. Now I think they have 5 V's. But the early 3 V's were volume, right? And the velocity and the variety. Right? So the data are generated in very big volumes. Every second, millions of billions of data are generated. Volume is very large. And then velocity, right? Speed is very large. and the variety, right? Different types of data. Earlier we had only something like discrete type, continuous type, and then qualitative, quantitative, and so on. Nowadays we have all types of data, even graphs, figures. All these are considered as data nowadays. For example, if you take X-ray, that is data. Right now, earlier days that was not considered as data. Now everything is data. So therefore, the variety is increased. So dealing with this large amount of volumes coming with the high speed with different varieties cannot be done using usual statistical methods, especially with the usual computing power. Right? But big data means these three things generally refers to data sets that are massive, complex, and generated with high velocity. Usually these are very unstructured data. You have to convert them into structured data to analyze and so on. Right? So that's what the big data word means. They are the main emphasis actually to improve the storage methods, how to analyze these methods and so on. That is where the big data experts are focusing on. Right? So typical examples we have already mentioned, right? It's generated everywhere. For example, social media. Uh, Whenever you type something, whenever you tick something, an observation is generated, right? So everywhere people are always ticking these things. So data are generated always. So these data are used always. For example, they know that once you tick something, they select something, somebody else will know what your preferences are, right? So when you're looking at say for example, a YouTube video, then automatically pops up a ad. They know what are the things that you always these ads are something that you like. So how do they know that what do you like? Because you have already given the data. And they use those data to pop up those ads when you are watching something. Right? The ad that you get is not the same as somebody else gets. Right? So they have the data already. You have given the data. I like these things. Right? You have ticked already. They have analyzed those things and they automatically come to your window when you see something. So those are things that done with the big data. Right? Sensor data, right? Sensors are everywhere, right? When you go in the road nowadays, we have here also, right? Traffic sensors. Right? So you can just sensor it and then you will find. Right? So like that, e-commerce websites, operating systems, servers, banks, and everywhere they generate big data, right? And then because of this big data, we needed something called machine learning. Right? We cannot do all these things manually or with small packages like earlier. Right? We need new things. So in the machine learning, the focus is usually actually to identify patterns in the data. Right? It's not like building a model and trying to fit the model. Earlier we look at some graph and then we think of a suitable model and then we fit that model and then use it to predict. In machine learning, modeling is not an important part. They just try because we have a very high computer power now. So they just try large number of different methods at the same time, almost the same time. So find out which method gives you the most accurate prediction value using the current available data. But they have some data there. So they use all these available methods quickly, and then see which method gives you the most close value to the available data already. So that's considered as the best method, and then use that method, and using that method, future is predicted. So that's what machine learning is doing. So this is applied in most of the situations like image recognition, spam filtering, recommendation systems like whatever I said earlier, like when you are watching a video, automatically ads come. So recommended ads for you specifically. Right? And then the data science is actually the combination of all these things. Right? Data science must have statistics, right? Statistical backbone theory is necessary. Usually, data science focus on big data. they use machine learning methods, right? And not only the machine learning, of course, in order to tackle with data science, for example, if data scientists are in every field, right? Data scientists in, say, for example, medical field may not be able to solve data science problems in finance field, right? So the person has to have a domain knowledge, right? The person has to have some statistical knowledge and also the machine learning knowledge, and whatever the field you are in, you have to have some domain knowledge about your field to apply data science. Right. So that's the end of this introduction here. So in this section, I briefly talk about, not briefly, actually I took more than 1 hour. We discuss about different views of statistics, what statistic is, and what I wanted to mainly emphasize is that statistics, of course, is used to analyze data and then come to conclusions about some large groups called populations usually. Whenever you make a decision, there's a possibility of error always. By applying statistical methods, proper statistical methods, what we try to do is to come up with decision with as small errors as possible, and also we want those errors to be small with high probability. Right? Not only without any probability statement, we want the errors to be small with high probability. So that is the main idea of applying statistical methods. Right. So this part is not actually in the book, that was added by me. Only the first view was in the book. So I'll give you that handout. I will send it by WhatsApp. So we'll come to the book now. Yeah. So book starts with, actually this is very unusual. In many of the books, they usually start with some other things. But this book directly comes to it. In a way, it's meaningful also, because if you look at the process of statistics, collection of data comes first. Right? And before you do anything else, you have to collect data. So as I mentioned earlier, in statistics, not the big data, but in statistics, data are collected mainly using two methods: right? Observational studies and experimental studies. So here we talk about experimental studies. Whenever you say experimental studies, there is some control or control made by the person who is doing the research. So that's why we call it the controlled experiment. Controlled experiments. So in this chapter and the next chapter, we'll be talking about, we'll be using some words here. So I have written down those words first here, and then when we talk about some examples, you will see where those words are used. Right? So mainly we'll be talking about some comparison methods in this case. Right? Here I'm going to stick to the book, not going to talk about, because there are so many other things when you talk about experiments. But here in the book they are talking about only comparisons of two things. Right? So method of comparison is the method that is used in that case. And then there is something called controlled and controlled experiment. Control is another word. Right? Control is an item or a person in the control group. Right? Usually when you compare, we call them treatments. Right? General word is treatment. It may not be a treatment in the sense medical treatment, but if you compare two things, two ideas, they are called treatments. So one treatment will be applied to one group, the other treatment will be applied to another group. So there are two groups usually. The group on which the treatment is applied is called the treatment group, the other one is called the control group. So control group, in that sense, that's the word control. And whenever there is a control group, then the corresponding experiment is called controlled experiment. Right? So treatment group versus control group I have already mentioned. And the treatments and treatment effects. Right? So generally we are interested in finding out or comparing the effects of two treatments. So we have to know what an effect means. So we will talk about that later. And then there is something called placebo and placebo effect. Placebo effect. Placebo is some again it's considered as a treatment, but it's not actually a treatment with some effect. It's a inactive treatment usually. And then randomized controlled experiments is another word that you will see. Double blind line design, and there is a word called bias and confounding. So those are some words that we will come across during this discussion here. And in addition to that, especially when we do some research with animals or humans, ethical considerations also come. Right. So in the book, actually, they have started directly with some example. And then using that example, they have discussed these ideas. So let's look at their first example here. They're talking about this Salk polio vaccine trial. This polio was a very big problem early 1950s in America. It is a contagious disease spread by person to person with contact. So it was one of the most feared illnesses, particularly among children. Often small children in grades 1, 2 and 3 were most vulnerable age groups. And then it was known that this is also there is a seasonality also. It was known that this polio usually comes to the peak during the summer and early fall. So those things were known things. So therefore people were trying to find, because it's a very dangerous one. You know why polio is, right? If you contact that one in the early ages, you can be crippled and so on. So it's a big problem. Right? So people were suggesting different solutions, different treatments. Right? Very earlier days, actually, people were even thinking that this disease was caused by the temperature, low temperature. Right? Some people were thinking if you eat ice cream, then it's possible to get polio. Right? Because there was some data, for example, in the summer seasons, usually you know that people eat more ice cream. Therefore, the ice cream sales go up. Right? And also, when they look at polio cases, they see that in the summer polio cases is also high. So some people even thinking that these things like cold things like ice cream is causing polio. There is something called association between these two. Number of polio cases associated with number of the ice cream sales. Actually, that was something called spurious association, not a real association. We will talk about those things later. Those are interesting things. But they were some people were trying to come up with real medical treatments. So there were some trials to come, because always usually these when you have medical treatment, usually they are tested with animals first. But of course, in order to apply to people, you have to test with people also. Right? That's a place. And at that place, actually, you have to get ethical clearance and so on. Even to test with animals, you have to get ethical clearance and so on nowadays. Right. Okay, so let's look at some designs that people use to test whether this new, there was a new treatment came up by this person Salk. That's called Salk polio vaccine. Right? Dr. Jonas Salk developed a killed virus polio. What do you mean by killed virus? Killed virus is a virus that was killed actually, it is inactive. So we inject this killed virus to the person, even though it is killed, still it has this ability to generate the immunity in a person, right? So immunity against this. So that was the, I don't know much about the medical stuff, but it's called killed virus polio vaccine. So it was required to test a field trial with people uh, to test the safety level, whether it's safe for people and also whether it is effective. So we need a research or some analysis or some comparison to see whether it is effective. So there were so many different types of proposals for the design, different types of designs proposed by different people. You can carry out it like this, you can carry out it like this, and so on. Different designs came up. But only two were accepted at the end, and then those two designs were carried out. So here we are going to talk about those two designs, the advantages and disadvantages of those designs. But before that, there were some known facts further, because when we do this vaccination is already produced, so we have to give this vaccine to children. But at that time of course nowadays also, in order to vaccinate some children, we have to get the permission of the parents. Right? So we can apply this test, or we can vaccinate only those children whose parents permit that. So that is something that we already know. Right? We have to consider when we doing this research. So that is one thing. Right? Children could be vaccinated only with their parents' permission. It was also known, there are some unknown things that means we have some information already. We have to use this information when we are planning our design. Right? We have already some resources. We have to use those resources. So one thing was, we knew that we have to get the people's parents' permission. Only those give permission can be vaccinated. And another thing that we knew at that time was something like this. It was known that children of higher income parents are more vulnerable to polio than children of lower income parents. So it was already known, using the data that was existed. It was known that the incidence of polio was high among rich people, higher income people, than lower income people. Later on they found out what the reason was. The reason was, in the lower income people, usually these children, usually they are in slums and very in houses there is no hygiene and so on. But that kind of children are immune to a lot of problems. They are immune already, right? So their parents are immune, and therefore this immunity comes to their children, and therefore usually these children in those places actually get only mild cases of polio. Once they get it, they have already immunization in their body, and therefore it doesn't go to very high levels. But these people who are rich are not immune to these kind of things. They don't go to anything, so they are protected by everything. So immunity is not there in their body, therefore they are contacted this virus, and effect is very large. Therefore they are affected hugely by this polio. Right? So there are that was also known. Right? Rich people have a high vulnerability than poor people. So we have to consider all these things when we select some people to vaccinate and do this research. Right. So let's look at what happened. What is the method they use? Of course, the method they use is called the method of comparison. It's a comparison. What are we comparing? We are comparing the people who will have this vaccination with the people who are not having the vaccination. In this case, those are the two groups. So those people who will have the vaccination is called the treatment group. The people who don't have the vaccination is called the control group. Right? So the people who don't have vaccination can be like this. They don't get anything. Or they may get a vaccination, but it's a bogus vaccination. It's called placebo. Right? One group, the treatment group will get the real treatment, real vaccination. The others will also get an injection, but that injection may have some salt water or something like that, right? Without any effect. So that is called the placebo. Placebo. Right. Okay, so there will be two groups. The method is called the comparison. So what are we going to compare? Right. So we will select two groups of people. So how the selection is done is important. We'll talk about that later. So we'll have two groups. We will give the vaccine to one group. The other group will be left without anything, or maybe with a placebo. And then what are we going to observe here? What are we going to compare? Can we compare the number of people who develop polio in this group and the number of people who develop polio in this group? Or can we compare something else? What do you think is better to compare? The number of people or something else?
You can't compare the number of people because you don't know if the populations are equal.
That's right. That's very good. Yeah, because numbers cannot be compared. Even the sample sizes can be different. You don't have to get exact size sample. If you have exact size sample, then you can of course compare the numbers in polio cases in the two the sample sizes. But it doesn't have to be like that. Sample sizes can be different. So therefore, what can we compare then?
Compare the ratios.
Yeah, you can compare the ratio or the proportion, right? Proportion of people in the first sample, that is the number of people divided by the sample size, and so for the second sample. So that is called the incidence rate, right? So that is the thing that we are going to compare here, incidence rate. So several designs were proposed, and two of them were implemented. The trials were carried out among children in the most vulnerable groups. So only the children were selected from grades 1 to 3. And there were some districts in the US where the polio was with a high incidence. Some districts there were not that much. So they selected only the districts where there are large number of polio cases. Right? So grade 1 to 3 and districts where the polio cases are high. So there were two designs as I mentioned. One design was carried out by National Foundation for Infantile Paralysis, NFIP design we call it. So what they did was they suggested to, now remember grade 1 to 3 are the vulnerable group. They proposed to vaccinate grade 2 students. Of course, in order to vaccinate, we have to consider only those children whose parents give consent. So out of those who are in grade 2 will be vaccinated. Grade 1 and 3 people whose parents give consent, as well as those people who, all the other people, even in grade 2, those people, parents who don't give consent will be put in the control. That was the design. So vaccinating all grade 2 children whose parents consented, leaving the children in grades 1 and 3 as controls. Actually, not only that, people see leaving the children in grade 2 whose parents did not give consent was also in that group. So that was one design. In that one, the control group doesn't get anything, right? They just leave left there. The group, the treatment group get the actual treatment. The second design was like this. The second design proposed selecting both the control group and the treatment group from the same population. Right? Now, what is the population from which we can select people here? First of all, the population is divided into two groups. One group is the people whose parents don't like giving treatment. The other one is the people who like. Right? So therefore, we cannot give the treatment to those who don't like them. So just leave them apart. So then now consider only the subpopulation whose parents will be willing to give this treatment to their children. Right? But then that subpopulation has to be divided into two groups. So it was decided to divide that population into two groups. One is the treatment one is the control. Children whose parents consented to vaccination was the population this was looking at. Each child was assigned one of the two groups. So first of all, how do we carry out? First of all, before we giving this thing, we have to divide this subpopulation into two groups. So that was done using a randomized method. That is very important. Right? It was not just decided, okay, this person will be in this group, this person will be in this group. According to personal preference is something else. Right? If you do that, there can be, even though we think we are randomly doing it, usually always possible that there is something called human bias. Right? Even though we don't think that we are not biased, usually it's always possible. Right? Because people have different preferences. Right? So the person who selects this into two groups may have some kind of personal preferences, and therefore the selection can be called bias. So therefore we have to use completely a randomized method to divide these two groups into, this population into two groups. So what do you mean by a randomized method? First of all, we can have, for example, list of all the children who are willing to get this trial or the medicine or the vaccine, and then ask the computer, right? For example, give a number to each person, say 1 to 5,000, say. So then the computer will select, for example, half of that randomly, and then put them all into one group. The remaining one will be the other group. So then in that case, it's called unbiased selection. Right? It's a random selection. Right? Personal bias will not be involved. So once you put them into that, so then still, then you don't involve in selecting which group will get the treatment. You can toss a coin, for example. Toss a coin and make that decide which group will get the treatment and which group will get the placebo in this case. Actually, placebo was applied in this case. Some other treatment without any effect, like salt solution or something. Right? So completely randomized methods should be applied to allocate the treatments into these two groups, assigning the treatments into the two groups. So one group was randomly chosen to receive, like using a coin toss or something like that. Random method, like putting two numbers in a hat and then mixing up and taking, okay, this group will take this one. And so you look at the piece of paper, if it is saying treatment, then you give treatment to them. Right? You don't decide. One group was randomly chosen to receive the actual vaccine, which is called the treatment, while the other group was given a placebo. So it was a solution of salt dissolved in water. So this kind of study is called a randomized controlled experiment. Randomized controlled experiment. Randomized because everything is randomized. Controlled means actually the person, the researchers somehow decide which group is going to get the treatment. So now we can discuss about the weaknesses and the strength of these two methods. So in addition to that, actually, now when you know that okay, this group is going to, the researcher knows which group is getting the treatment and which group is getting the placebo, but the children did not know. Children did not know whether they are getting the actual treatment or the placebo. So therefore, that we say it's a blind experiment. Right? Blind in one way, in that case, children didn't know. Children are blind to the fact that which treatment they didn't know which treatment is, whether they are getting the treatment or the placebo. On the other hand, after this treatment is given, after the experiment, after some time, somebody has to decide whether these people have developed polio or not. Right? So this after several months, every person was checked to see whether these persons have signs of polio or not. So that's usually done by doctors. So doctors also didn't know whether this person has got the treatment, real treatment, or whether this person has got polio. So therefore, actually, this one is blinded by in two ways. It's doctors don't know, and also the participants don't know. So it's a double blind study. double-blind study. So what happens if they knew, for example, if the children knew that they, for example, some people knew that they were actually getting the medicine, and the others knew that they were not getting the medicine, what will happen? What would happen?
The mindsets will be different.
Yeah, mindsets will be different.
Parents would come.
Yeah, parents will also come. Will be very worried and so on, right? We wanted them to be vaccinated, but you are not doing it. Right? So all these problems can occur. Actually, as far as the outcome is concerned, as he said, can have some effect or mental effect. Right? Not only not the actual treatment effect, but there can be some mental effect also. Right? If that was happening. Right? So the mental effect in the two groups can be different. Right? Those who know that, for example, we are getting the treatment, probably they are going to be now less careful. Right? If they will be going everywhere, they are not wearing these things, whatever the mask and so on, because they know that they will have the real treatment. Probably, ultimately, their incidence rate might be higher than the other one. Others, right? So that could happen. So that means there can be some confounding factors, right? Confounding effects. So in this case, mental effect, for example, can be confounded with the real treatment effect. Right? We want to find out only the treatment effect. We want to find out only the treatment effect. But it can be confounded with some other effects, for example, mental effect. What happens if the doctors knew which group is this? For example, when you are examining a person, you know that this person really got the medicine, the other person didn't get the medicine. Then what can happen?
You might be biased towards giving.
That's right. So again, for example, if the doctor knew that okay, this person has got polio, the real medicine, he might not even check it and say, okay, he has got the medicine, so it's not possible for this person to get polio. So he will say he doesn't have the polio, even if he has. Right? So there can be that kind of bias in the decision, and that again gives you some kind of confounding factor. Confounding with the real effect. Right? So in order to remove these things, we have to actually definitely do this kind of blind experiments. Otherwise, this different kind of confounding can come into the experiment, and therefore we will not be able to really check whether this thing has a real effect or not. Because what we will observe at the end is the treatment effect as plus some other effects, all combined together, mix up together. Right? We cannot separate the treatment effect. So in any good experiment, we should be able to separate the real treatment effect, right, from the other ones. So therefore, it is always best actually whenever you do this kind of a comparison test. A treatment group and the control group will be almost the same in every aspect except from the treatment. Right? So then, even if there are some confounding effects, the confounding effect will be in both groups. And therefore, for example, if we, now in this case, the treatment effect will be, for example, the difference between the incidence rates. Right? So when you take the incidence rate in this group, that incidence rate contains the real effect and the confounding, some confounding that can be there. But it has the real effect of the treatment plus some confounding. And the other one will have a treatment effect of the placebo plus the confounding of the same factor. Right? So when you subtract, right, from the incidence rate here, this one from the other one, the confounding factor will cancel out. So it will have only the treatment effect from this one minus the treatment effect, whatever the effect of the placebo. So therefore we can separate out the treatment effect. That is what you should do whenever possible when you are comparing. We have to have this control group people and the placebo group or the treatment group should be the same, almost the same, with respect to whatever the factors which can contribute to the result, except the treatment. Right? So, for example, in a simple example, suppose you want to compare two fertilizers for chilies. Right? Suppose you already have some fertilizer that is used by usual farmers. and a new fertilizer has been developed. So this new company says if you put our fertilizer, the same amount that you're using right now, but the yield will be higher. Right? So if you want to design an experiment to check whether this person, whatever this person is telling is truth or not, how would you design the experiment? Suppose these are for chilies. Right? So will it be suitable? For example, I give all fertilizer to him, and then the new fertilizer to him, and suppose ask him to go and plant some trees and put this thing, and you also do the same thing, but in your place and in your place separately, and then find out how much chili yield you got. If you do that experiment like that, what will happen?
It will be biased because the way he plants and
That's right. Because not only the fertilizer is affecting the yield, there are so many other factors which affects the yield, right? For example, soil condition. Right? Soil condition in your place might be completely different from his place. Right? So that effect is going to be confounded with your fertilizer's effect. His soil effect is going to be confounded with his treatment effect. Mixed up. We cannot separate. There will be effects from whatever the amount of water you put and whatever the amount you put, right? Sunlight, so many other factors. So therefore, you cannot actually, even if he finds out actually his yield is higher, right? We cannot conclude that that higher yield was given by the treatment because of the treatment, because there are so many other things. So therefore, whenever we do this kind of things, so in that case, his thing will be the treatment, you all will be the control. But the control group and the treatment group must be all more the same with respect to all the variables that affect the outcome except the treatment. Otherwise, there will be always confounding, and therefore the result will not be valid. Right. So this experiment was the double-blind experiment. Therefore, it is called double-blind, randomized controlled experiment. Double-blinded or double-blind randomized controlled experiment, and those are the best ones, if possible, whenever possible, for you to apply if you are doing a comparison study. Right. So these are the data that we have here. Actually, got them by these people. The first one, double-blind, randomly controlled experiment. In the treatment group, there were 200,000 people. Out of that, this rate is given for 100,000. So 28 for 100,000 got the polio. That is in the treatment group. In the control group, there were 200,000 people, but there are 71 got 100,000 cases. Among those who didn't give the consent, there was this amount of polio cases. Right? So these are the data. Okay, what happened in my table in another again some category. Okay, I think we will go quickly. Yeah. So these are the numbers. So this last column is out of my. So what can you say? This is the randomized double-blind one. This is the other one, NFIP1. So the rate for the treatment group is of course smaller, much smaller than this one. If they were just very close, like 28, 25, We would have said there's no big difference, but of course in this case there's a big difference, right? There is also a big difference, 25 and 54 in that one also. But if we didn't do this one, if some people did only this one, by looking at this thing, can we decide that the treatment is effective? We cannot really say that treatment is effective, even though this number here is small and this number is large, because we don't know whether this reduction was really done by the treatment or whether it was done by some other factor, because there was no control. There was no randomization. Right? For example, grade 2, now this polio, as I mentioned earlier, is a contagious disease. It goes by children to children, right? By contact. So, for example, the first grade 1 children may have some amount of exposure, right? They are connected to each other at a certain level. Maybe when you go to grade 2, there may be more connection because there are more friends, right? When you go to grade 3, maybe that exposure can be even higher because many people are contacting with each other, right? So therefore, the exposure level is different in these 3 groups. Give me a second. Groups are considered in this study. The amount of exposure was different, right? Like the amount of sunlight getting in the 2 experiments were different. Here, the amount of exposure was different, right? One group only grade 2, the other one grade 1 and 3. So there can be different exposure, and that may have an effect, exposure effect. So those 2 exposures are going to be confounded with the treatment effect in that case, and also the placebo effect separate. We cannot control them. But in this one, the treatment group had 1 to 3 all students. The control group also had 1 to 3 students. So whatever the exposure is similar, right? Same sunlight, same water, like that. So that is one thing. Another thing is that in the second group, the age, right? Remember, we told you that this is young people, young students are the most vulnerable group. The young age students are going to get higher rate of incidence. So there maybe, we don't know, maybe there is an age effect also. Right? Grade 1 is the lowest age, and grade 2 is the next stage, and grade 3 is the third level. So maybe if the incidence rate is going down or going up with the age, there is an age effect. Right? So this group has only grade 2 in the treatment group, the other was in the control group. So therefore, if you look at the age, the 2 groups are not similar in terms of age. They are not homogeneous, we say. They are not homogeneous in terms of the variable age. They are not homogeneous in terms of the variable exposure. But in this one, treatment group has all the age groups 1 to 3, and also they have the same exposure groups. And similarly, control group has the same. So therefore, in this experiment, except the treatment, whether they get the actual treatment or the placebo, except that fact, all the other factors were similar within the groups. But here, they were completely different. So therefore, even though we see that there is a big difference in the incidence rates for the vaccine group and the other group, we cannot take this small number as evidence for the treatment. As evidence telling that the treatment is effective, because we don't know how much large the other effects are. Right? So therefore, that is a very important thing to understand. Right? So therefore, whenever we design the experiment, we should design so that there will be no confounding factors. It's a very important. In order to do that, what we can do is actually, this is not, even though we say this thing easily, it's not easy to do this kind of things always. Sometimes it's possible, sometimes not possible. But whenever possible, try to select the 2 groups so that they are similar or homogeneous with respect to all the variables that are going to be related to the outcome, except the treatment. Right. So that was a very good thing came up with this experiment. So you can read the book. There are a lot of details here. So I have given this explanation here. You can look at the notes. So now look at, here I have shown it using a graph also, the possibilities, because there can be an age effect, there can be exposure effect. Age effect and exposure effects are different in the two groups in the NFIP design, whether they are the same in the other design. Right. So please read that from the book and also from the note. Okay, now here I am asking a question. This is not a difficult question. Okay, now suppose you could have done something like this. What would happen if all the children whose parents consented were given the actual vaccine, and those who were not those who didn't give the vaccinated, those who didn't give the consent, will be taken as the control group. If that was the design, what will happen?
It's again going to be biased because the reason that they didn't give their consent might be because they were sick or they were rich or something like that. So even that factors might affect the experiment.
Yeah, remember earlier I told that those people, those children whose parents are rich are more vulnerable to this thing, and therefore they will be more likely to give consent because they know that their children are going to be get polio with high probability because that's already observed in the field. Therefore, they might give their consent. Therefore, if you do this one, those who getting those who are getting the vaccine, maybe most of them are going to be rich people, right? Whereas in the other one, maybe less amount of rich people and all the other people will be poor people, and therefore, if there is any effect due to this fact, right, social status, and we don't know whether there is an effect because of that, right? Because at the beginning, for example, there can be different in terms of the immunity, right? Poor people, as I mentioned, have immunity already, right? So therefore, they are going to get less incidence rate usually anyway, right? So the rich people have poor immunity, and therefore they at the beginning to start with, they already have a high rate of possibility of getting vaccine, getting a polio, right? So therefore, then there is a big confounding factor there, right? So therefore, that kind of design will not be good. Okay, so answers. So when you have this confounding factor, we say factors are confounded. So for example, there is an effect due to the factor. Factor is the treatment or vaccine. So there is a variable. The variable can be denoted as 1 and 0. 1 if you get the real treatment, 0 otherwise. So the other way around. So it's a factor, right? This kind of variable which has 2 groups or 3 groups called a factor. Then there is another factor called age factor, right? Grade 1, grade 2, grade 3. Right? Maybe the exposure factor is also a factor, right? Amount of exposure, we cannot give a numerical number, but we can say grade 1 level exposure, grade level 2 level exposure, and grade level 3 exposure, and so on. So there can be, we say, confounding factors. Factors are confounded. So when the factors are confounded, the final result we say it's biased, become biased. Result can be biased. So what do you mean by bias is that there is a answer that we should get if there was no confounding, right? But because of confounding, we are going to get either less value than what we should have obtained, or a larger value than what you should have. So there can be a negative bias or positive bias. So when we say we use the word bias usually, if that can happen, even if we do the same experiment with different type of different sample. So that means always, if we repeat this experiment, if we have, for example, if you are going to get an answer which is going to be less than the actual answer that we should have got, always, then we say our answer is negatively biased, less than. So therefore, this biasness actually have some idea about what will happen if we repeat the experiment. Right? We tend to get always consistently or systematically less than what we should be getting, or maybe in some other experiment it may be always higher, right? Higher than what we should get. For example, we take a very simple example. Suppose we are measuring the length of something. That's an experiment. Right? Suppose our tape is cloth tape. Now it is stretched, right? So if, for example, we are measuring something that has 20 centimeters, because it is stretched, always we are going to get a number less than. So it's always, whoever the person who measures it is always going to get a less value than the value actual. So that is called a bias. Right? But if you have a real measurement instrument, suppose one person gets 20.1 inches and the other person gets something less. Different people can get different values, but one person can be low, one person can be above. That is not bias. That is just an error. Right? So in that case, if the error can be negative or positive with the same probability, we say we have unbiased situation, unbiased. But if we have, for example, stretched this thing, then always is going to be biased. The value is going to be biased. So the same idea here. Right? If the answer that we are going to get because of this confounding is going to be less always, or with high probability, than the actual value we should have got, we say negative bias, otherwise it's positively biased. So anyway, usually when you have confounding, we almost always have bias. So this is called the confounding bias. Biases can occur not only for the confounding, it can occur for some other reasons also. But the bias that occurs because of the confounding is called confounding bias. Now there is another thing that there can be bias. That is called placebo effect. Placebo effect. So the bias occurs for the placebo effect is called placebo bias. Now, suppose, for example, person we give a treatment. The person doesn't know whether he has got the treatment or not. So suppose it's a blind one. So in that case, the person, even the person who gets the treatment, and also even the person he gets, even if the person hasn't got the treatment, they don't know whether they have got the treatment. Everybody is thinking that they have got the treatment. Everybody is thinking that they have got the treatment. So there can be some mental issue, mental effect. Because of thinking that they are getting the real treatment, and therefore there can be some kind of relief. For example, for painkillers, they have observed this kind of effect. Right? You give, for example, real painkiller to some people who have been, say, operated on, done some operation, and give the say placebo, something else, without any effect to other group of people. But both group of people may observe some kind of relief. So the relief they observe is not because of the treatment in that case, because of the mental effect. So that is called the placebo effect. Placebo effect. So if the placebo effect is occurring in the both groups, that is fine. It will be cancelled out. But if the placebo effect is occurring in only one group, that will not be cancelled out. That will be confounded with the real effect, and therefore the result will be biased. So that is another one, placebo effect. So in the book there are some other examples. One other example is called the gastric freezing experiment. You can read these things in detail. What in this chapter, what they are trying to show is actually this confounding thing, right? And how to do a completely randomized experiment, controlled randomized double-blind experiment. So in this experiment, let's see what it was. In the 1950s and 1960s, doctors developed a procedure called gastric freezing to treat peptic ulcers, right, in the stomach. When they have ulcers, this was a method developed to treat that. The method involved inserting a tube filled with very cold liquid into the patient's stomach with the idea that cooling would reduce acid secretion and allow the ulcer to heal. So what they did was they inject or not inject actually insert some cool liquid into the stomach, and then the things inside the stomach will be frozen for some time, short period of time, because in that case when it is frozen, the acid will not come out into the stomach, and therefore the ulcer will be healed. That is the method. So they applied this to two groups. One group was the treatment groups for the people who really did this. The other one was oh no, this is a okay. This is early uncontrolled studies suggested that many patients improved. Right? So earlier they only did it to people who are really suffering from this one. So for example, if they did it for 10 people, and out of that, say 7 people say, okay, we are feeling better, so they consider it to be a good reason, and therefore they say, okay, this method is working. Right? If out of 3 people only, out of 10, only 3 people succeeded, they would not say. But if they more than 5, for example, out of 10, they would say, okay, this is a successful method. So that was their observation earlier. Without any control, they gave it to only the people who were suffering from this ulcer, and they found out that more than half of the 50% of the patients were saying that they get relief, and therefore they were telling that it is successful. But some people didn't believe this result because there was no control. Right? There was no control group. They were just not comparing with the control group. Therefore, some person called Banneheka carried out some compared gastric freezing experiment. In this case, the real treatment was done, and also something called sham was inserted into some of the control group. This was not the real freezing thing, but something was inserted, but that was not actually freezing the stuff. But the patients didn't know what it was. So it was a blind experiment in that case. So result in this one, result showed no improvement. Right. So let me show, do I have the data here? Yeah, so this is the one. So earlier, when they did with no controls, they did it with, say for example, there were 24 plus 31, 32. So out of 32, 24 said there were very marked improvement. Out of that, 7 said there was a moderate improvement. Only 1 said no improvement. So when you look at that thing, it's giving like a pretty good evidence that the method is working. Very large amount of papers, percentage, if you consider percentage, large percentage is markedly improved. Yeah, 7 moderately. But and then there was some control experiment with control. That means there are 2 groups. In this one there is only no control group. This one there was a control group, but it was not randomized. Right? Those people who are getting the real treatment and not getting the treatment were not randomly decided. Right? So in this case, what happened actually was doctors have finally found out that doctors have done this procedure for those people who are not really extremely sick. They have this ulcer, but it was not very serious. Right? Those who were serious was not for those who were really serious. This treatment was not done given, right? So therefore, in that case also they saw that because this treatment was given for people, normal people usually, and not they are not really sick, right? So after that they were saying that people, out of 15 people because of the market, they were just telling that we feel better, and 3 were saying we are feeling moderately better, and only 2 said we didn't get any improvement. But when they did a randomized control, right, so that when the physicians decided who is going to get this treatment, so in that one, there were really sick people and also moderately sick people inside that group. The other group also had the same type of people, therefore, real comparison. In that case, also, actually, there were only 4 cases in that case. That is a big problem in that case because the data is sparse. But even with that data, there were now 0 market ones and only 1 moderate one, 3 none. Right? So this is bigger than this one. Right? So therefore, with this, we cannot actually, even though these numbers show that there is similar, suggest that there is an improvement. It's not a real improvement. We cannot conclude. It may be a real improvement, but we cannot conclude so because the experiment was not a randomized controlled experiment. Right? Because there can be a lot of confounding here, especially for example in this case, people knew that there was a confounding. The treatment group was not a seriously ill people. They were mildly ill people. Right. Okay, so I'm not going to explain all these things because these all are explaining similar ideas here. Please go through the note, and also I have included these things in the note. We don't have time to go to the second chapter, so we will do it the next week. We are doing only one day, right?
Yeah.
Okay. So I think this is a good place to stop because I don't have time to discuss the other one also. We will discuss this thing this time. So please, are you using a book for the other course also?
Yeah. For real analysis, we are using real analysis by Terence Tao, and for linear algebra, we are using linear algebra by Michel Lennox.
Okay, so how does it go usually? Does he give the lecturer give you note, or does he give assignments or what?
Stop the recording.
No, not recording. No, you stopped recording.